So this, or the first part, asks us to make an equation. So we're letting R represent the speed at which Lassie can run. So it's the ends up being the rate Lassie runs when we derive it, and S represents the speed at which Lassie can swim, which ends up becoming the rate at which Lassie swims when we derive. And we have Ty represent the time it takes Lassie to get to the drowning person, given that she jumps at the point of water at point D, which is y meters from C. So the distance from D to C is y. And then we find the value of y that minimizes Ty. So we're going to do an optimization problem and provide a complete interpretation. So the time it takes Lassie to reach the person only changes as y changes. So to find the minimum, we end up making this equation right here, which is Ty equals the square root of y squared plus x squared over s plus 2 minus y over r. So z minus y equals the distance that Lassie runs on the beach, and the square root of x squared plus y squared equals the distance he swims in the water. And we know the equation for distance is rate times time. Therefore, time equals distance over rate, which is why we put these over the rates of s and r to get our equation. So to find the minimum time it takes Lassie to reach the person and how far he should run down the beach before jumping in the water, we took the derivative to get it, and then we set it to 0. So this will be the minimum point of our function. So we start by doing the power rule on, the product rule on this side. So we end up getting 1/2 times y squared plus x squared to the negative 1/2 times d over dy times y squared plus x squared over s. And we use implicit differentiation here. And then you add according to this equation, and you use implicit differentiation again to get negative d over dy times y plus plus 0 over r. And then we just simplify to get a derivation of y over s times the square root of y squared plus x squared minus 1 over r. And then we set to 0. And then once we set to 0, we solve according to y. So we multiply this we add 1 over r over to get 1 over r, and then we multiply by s down here to get s over r equal to y over the square root of y squared plus x squared. And then we cross multiply over to get r over here, and then we cross multiply this to get this portion over here to do s times the square root of y squared plus x squared equals ry. And then to cancel out, we make sure to set it to 1/2, and then we square both sides to get y squared plus x squared equals ry over s squared. And then we multiply over it again to get s squared y squared plus x squared s squared equals r squared y squared. And basically we just simplify down to get to our equation of y equals sx over the square root of negative s squared plus r squared. So we solved for y, and this equation can be used to find y to minimize the original function. For this to work, Lassie's running time has to be faster than her swimming time, so over down here. So if we look at the denominator, when r is greater than s, we get the same root. We get a root of a positive number, which will result in a positive solution. But if s is greater than r, we get a square root of a negative number, giving us an imaginary number. Therefore, the dog should run longer than he swims in this equation, or in this diagram. So it should run for a longer time than it swims to make sure that our equation of y equals here works. So basically we started out by using this diagram to create the function that relates time it takes Lassie to get to the drowning person to the distance the drowning person is from Lassie. So this is that equation that we created to eventually derive, set to 0, and find our minimum time for how long. And we will use this to determine how far Lassie should run down the beach before jumping in. Abby, you're up.
Alrighty. Are we just gonna keep going?
Yeah.
Okay. So the second part of this problem gives a data set that gives the times that this dog ran on land over a distance of 20 meters and the times that the dog swam over a distance of 10 meters in order to reach a ball in the ocean. So, averaging all of the running times, the average running time was 3.148, and the average swimming time was 11.464. And then you divide the distance run by the time it took to run to get the velocity, which was 6.35 meters per second, which is the running rate. And then you take the distance swam, which is 10 meters, divided by the swimming time, which is 11.464 seconds to get the velocity of the swimming, to get the swimming rate, which was 0.872 meters per second. And then we take the original derivative equation found in the problem presented by Evan, and plug in these two numbers into this equation in order to get this equation, which is the derivative of t of y is equal to 1.1474 divided by the square root of x squared plus y squared minus 0.157. And then in order to optimize the relationship between y and x, you set this equation equal to 0, which I did over here, and then essentially you just simplify. So I multiplied both sides by the square root of x squared plus y squared, and then divided by both sides by 1.147, and then squared both sides to eliminate the square root on the x squared plus y squared, and then distributed this number, and then just subtracted the y squared values, and then square rooted that number in order to get the equation y equals 0.138x. And this equation shows the relationship between x, which is the distance swam, versus y, the distance run. And it shows that y, the distance run, is 10 times greater than the distance swam. And this equation allows us to determine the point at which the dog enters the water. I'm done.
Okay, so for part 3, this is a graph representing Elvis the dog, optimal relationship of x and y, x against y, and this is Pennington's data points plotted with the line using Abby's equation, y equals 0.138x, which is a positive correlation. As we can see, the data points are pretty near to the line, which indicates that there's an optimal, this means that Elvis is able to somehow optimize the time it takes to get the ball. However, like the data shows, less than about like 12 meters to 0, Elvis is able to optimize the time better than what when the distance is 12 to about 20. So the further the ball is away from the shore, the data points stray further from the line, and which means Elvis can eyeball and optimize how far he should run from the beach, which is y, before jumping into the water through trial and error, but does not indicate that he can do calculus, or that we don't know that he can do calculus.
Are you ready? Part 4. Okay. Yeah.
Well, I can just say it over here. Pennington assumed Elvis's running and swimming rates remained constant throughout the experiment. This may be true over small distances, but in reality the dog would have likely tired, slowing the rates over time. For a more thorough analysis, and to account for the limitation, Pennington could have made use of assistants. He could have equipped them with stopwatches to record Elvis's running and swimming times for each trial, instead of simply assuming these rates were constant throughout the entire course of the experiment. Using assistants would have greatly improved the quality of the data Pennington collected.
As your in-house animal behavior expert, I would like to emphasize that this problem and all of this math that we just performed does not indicate that this dog knows how to do calculus. It indicates that the dog is able to optimize the time it takes to reach an object floating in the ocean, most likely through a trial and error process. Thank you.